Our planet has a moon that sometimes shines brightly in the sky as a full moon, and other times looks like a crescent. Have you ever wondered why the moon has different phases? I'm Science Mom.
And I'm Math Dad.
Today we're going to explore how our planet moves through space with two art projects. Hello and welcome! Today we're going to be talking about how our planet rotates through space, and we're going to do it with exploring two fun projects that you can do, a chalk sundial and some moon art. Quick shout out to...
Moon. We're on the wrong planet.
We are on the wrong planet. Let's go to the moon. While Math Dad is moving us to the moon, quick shout out to Kendall watching from Illinois. I see Aubrey and Yana, Science Mom Amber. Now we're in a green world. And here is the moon. We are on the moon. Hello to Cassidy from Mississippi, to Rebecca and Corinne. Happy Friday.
Oh, I'm excited. Lots to get through today.
If we really were on the moon, this would be a problem because we would not have an atmosphere, and Math Dad and I would both be in dire need of spacesuits.
But while we're talking about the moon, real quick, what type of rocks are moon rocks? Are they sedimentary rocks, igneous rocks, or metamorphic rocks? Quick, throw your answer in the chat if you have. I don't think we talked about it in class.
We did. We'll see if they remember.
Oh, did we?
Hello to Amaya in the UK. And let's dive right in. I am seeing, Millie says cheese. The moon's not made out of cheese. Ibrahim says igneous, and igneous is correct. Moon rocks are almost entirely igneous, and this leads right into one of the answers to a question that came up last time. And the question was, what are the oldest rocks? Well, if you were on the moon and all of the rocks on the moon are igneous, and then all of a sudden you came across a piece of feldspar that had a lot of quartz in it, mixed in with it.
That would be pretty surprising.
It would be really surprising. It turns out one of the oldest rocks is actually a big rock that was brought back from one of the Apollo missions. It's nicknamed Big Bertha, and it's thought to be one of the oldest Earth rocks around, but it was found on the moon.
Oh.
Kind of crazy, right?
Yeah.
All right, quick correction before we get into answering those questions. Last time I said that I said that talc was the same thing as chalk, and that is incorrect. And sometimes this happens, especially if you're teaching live. In my mind, when we got to talc and talc is soft, I was like, I think talc's the same thing as chalk. I remembered incorrectly. Talc is a soft clay mineral that has a lot of magnesium in it and silicon.
So it's soft like chalk, but different.
Very different than chalk. Chalk is actually a soft type of limestone. It's almost entirely calcium carbonate. So quick correction to that. And then the next thing I wanted to do was answer the questions that came up last time, because we had two great questions. One was, what is the rarest rock? And it's easier to answer what the rarest mineral is. The rarest mineral on Earth is actually called Painite.
What?
It was first misidentified as a ruby. It does have a red color like a ruby, and there are only two existing gemstones of Painite that have actually been cut into a gemstone shape. And finding it raw like that, that's a raw piece that has not been cut, it is by far the rarest mineral on Earth. It looks quite a bit like a ruby and has a similar hardness too.
Oh, interesting.
Yeah. And then the oldest rock question. This was a great question. What are the oldest rocks on Earth? There are several different rock formations that are all competing for oldest rock in various locations around the world. All have been dated to about 4 billion years old. But Big Bertha, they actually think is a piece of Earth rock that when the moon and the Earth first collided, part of the Earth rock got left on the moon. And that's how we ended up with some Earth rock on the moon.
So the Earth is like 4.5 to 4.7 billion years old?
Yes.
What in the world is this next to it? This Murchison?
So if you'll move us real quick so they can see the rest of that word, it's a meteorite.
What?
So the oldest physical rock on Earth actually did not come from Earth at all.
Because it's older than Earth.
Because it's older than the Earth.
Oh, mind blown.
So a famous meteorite that fell in Australia in the 1960s, its fall was observed. It's been studied very closely, and it is dated to be about 7 billion years old, older than the Earth.
Crazy.
Amazing, right?
That is amazing.
Now, let's get right into talking about sundials.
Ooh.
So I've got a quick question for you guys. If you're watching live in the chat, put your answer in the chat. And if you're watching the replay, just say it out loud. When will your shadow be the shortest? And when will it be the longest?
Ooh, that's like what time of day?
What time of day will your shadow be the shortest?
I think I know the answer.
Great joke in the chat from Millie. Painite, it must be a pain to find it. The scientist, that would be a great story for how it got its name.
You have to go to great pains to find it.
The scientist who discovered it, his last name was Pain, and that's why it's named Painite.
Oh.
Yeah.
Makes sense. All right.
Noon. Diamond Star says noon. RT Guy says shortest at noon. Kara Rogers says shortest at noon. Noah says shortest at lunchtime, and that is correct.
That's got to be right, because when the sun is as close to overhead as it's going to get, that's when your shadow will be as short as it will get.
But it all does depend on what part of the time zone that you're in. Because really, if we used sundials for clocks, then noon would be a little bit different here versus 20 miles from here versus an hour's drive from here. But we consolidate into time zones. We live near Las Vegas, Nevada. We're right at the edge of our time zone. So I'll show you in a minute, the chalk sundial that we did, the shadow was shortest closer to 1 o'clock p.m. than at noon.
Yeah, pretty cool. So somewhere around noon, but not at exactly noon.
Depending on where you are in your time zone.
Yeah, that makes a lot of sense. Okay, so if we jump over to my slides here, here is a sundial built by Science Mom Eliza.
And you can use anything to make a sundial. In this case, Science Mom Eliza used a skull they had to make the sundial. You can see the shadows are longest in the evening and then shortest at noon.
So they put the skull right here and then just traced the shadow every hour throughout the day. And that's what we got.
That's what we got. And then here is a sculpture of an ibex just showing how different the shadow looks at different times. This is right around noon. And since we're not down by the equator, we don't see just, no shadow. And then here we have right at sunset, and look how long that shadow got. It's totally stretched out.
Yeah, very, very different shadow. Okay.
Now here is the one that we made with Math Dad.
All right, so we marked a spot on the ground where I was supposed to stand every time, and then every single hour we came out and we traced my shadow.
And you can see that the shadows started out long in the morning at 8 a.m. and long in the evening at 5 p.m. But then as we got closer and closer to lunchtime, they got shorter and shorter.
So here, Science Mom even colored it all the way in.
I did.
All pretty like, aw. So then if I want to know what time it is, I can just go stand in my spot and we can read the sundial from there. So yeah, here's a picture of us when we were making it. It can be hard to stand still and get the shadow traced right.
It is, but this is a really fun project, and any object you do will look different. So now we've got a question for you guys. What time is it right here? Where Math Dad's standing holding our puppy.
Can you read this sundial? Did we make it understandable? Mm-hmm.
Science Mom Amber said it's like a Math Dad peacock. And it kind of does look like a peacock. So the shadow falls between 11 and 12.
Oh, you can't give him a hint, Science Mom.
Oh, that was just a tiny hint.
Oh, no.
Elizabeth says 11:30. She says 12:30. Eleanor says 11:30. And it was 11:35. Is that right?
11:34.
11:34.
According to my phone at that exact moment when we took the picture. So yeah, good job, those of you who read that. I imagine it's much harder with a sundial to get the exact minute right, but you can get pretty close. So yeah, good job.
You can.
Seeing those guesses come in. All right, here's one. That one's actually going to show up later, though. So
spoiler alert.
Spoiler. Okay. All
right, let's talk a little bit about why the shadows change and what this has to do with the moon. Because our planet is rotating around the sun. And as it rotates around the sun, it is spinning. And it's the spinning of our planet that gives us day and night. And as we spin, the sun changes location in the sky relative to us.
That's right. So from our perspective, it looks like the sun's going around us, but it's all
really
relative motion. Yeah, that's right. So it's not the fact that we're going around the sun that was causing those shadows. So the Earth is spinning, it's turning circles itself as it goes around the sun. I'm moving my finger, but it spins in place. But as it goes around the sun throughout the year, we're seeing we have 365 rotations, and actually it doesn't quite work out that way but yeah.
Yeah, that's a topic for another time. So when we are facing the sun, we have day. When we're facing away from the sun, the planet has rotated around. That's when we experience night. But the moon has day and night as well. But our moon is kind of special because our moon is locked with our planet. So we call that
tidally locked.
The same side is always facing Earth. And if you look up at the moon, you'll notice you can see certain craters and shadows on the moon because of old meteor impact sites on the moon.
And they always face the same ones are facing us. That's the crazy thing. So the Earth is rotating as it spins around the moon, the sun, but the moon, it's going around the Earth. It is not rotating. The same face is facing the Earth the entire time. So it's not quite the same thing going on.
So are you ready for a quick little art contest, Math Dad?
Yeah.
All right, let's switch our camera view real fast. We have a printout in the end of the notes that you can print, and you can color with white crayon. And the cool thing about coloring with white crayon is that crayon is waxy, and that means it is not water soluble. It's not going to mix with water. So if I color in this really well, I colored in yours too, Math Dad. You ready?
Oh, yeah.
Now we're going to see who can make their moon appear most clearly.
No, just a sec. So you're coloring in the darker part?
Coloring in this darker part right here.
The darker part. And, that's interesting. So that's darker right now. Maybe you tried to sabotage me. I'm coloring again, Science Mom.
And it's a good idea to do several coats. And now, as we paint across, it's like the moon appears. See that? See how my moon is appearing?
Whoa. So what's happening there? Why is the moon appearing?
Now I have a crescent moon. And it's because the crayon does not absorb the water. And so as I color across, the paper absorbs all of the watercolor and the crayon does not. And then if you want to even, you can kind of wipe it off with a finger or a paper towel, and it's even cleaner. So there's my crescent moon. Next, I'm going to do a half moon. And Math Dad has a cheaper brush that will be maybe just a tiny bit more challenging.
Whatever.
But I'm sure the chat's cheering you on, Math Dad.
Huh.
Isn't that satisfying?
I don't know that mine worked as well.
We can't all be superstars.
Oh, Science Mom. I think you sabotaged mine. So you did something. All right, here goes. Ooh, I don't know. That's looking a little better.
So this is a fun way to explore the different phases of the moon. Here we have a crescent moon. Here we have a half moon. Ibrahim says, "You can do it, Math Dad." Kunalyn says, "Go Science Mom." I love it.
You're going down, Science Mom.
But we don't have time to do this whole thing live.
You don't think they want to watch me struggle to...
No.
No?
Nope. I think they've seen enough struggle, and it's time to talk a little bit about why we have phases of the moon. What causes the moon to sometimes look like a crescent, sometimes look like there's half of a circle in the sky, and sometimes look full? Why do we sometimes have a full moon and sometimes not?
It's a really good question, and I think a lot of people would wonder that, or they just take it for granted. Sometimes you see more, sometimes you see less, sometimes you see no moon at all.
And that is because of how much of the moon is getting sunlight. When we see part of the moon as a crescent and then part looks darker, what we're seeing is that part of the side of the moon that faces us, part of it is day and part of it is night for the moon. So let's take a look at this little graphic right here. So when we see a full moon, you can think of it as like here's the moon, and the side of the moon that is facing the Earth is completely facing the sun. But when we see a crescent moon, then the side of the moon that is facing the Earth, only part of it is getting sunlight.
Wait, okay. So you're saying the sun is up here, it's shining on the moon, and that's why this top half of the moon is all lit up. But from here on Earth, when we look at it, we're only seeing this half that's lit up.
Exactly. And Isaac has a great question. Why does the moon sometimes look orange sometimes? And that has a little bit more to do with the light as it's reflected and coming back to Earth. So the moon can look orange for a couple of reasons. One is if there's a lot of wildfires or other things putting up smoke and small particles into our air, that filters the light and will make the moon look a little bit orangish. And the other is if there's a lunar eclipse. So if right here, when we're seeing a full moon, the moon is not in the Earth's shadow. But if the moon gets into the Earth's shadow completely and we get a lunar eclipse, that will cause it to look a little red.
Okay. And so often, or rather, in general, when we see a full moon, it's not perfectly behind the Earth, but probably pretty close.
Yeah.
And so we don't see the Earth's shadow, but you're saying the eclipse is caused by the Earth casting a shadow onto the moon.
Exactly. And then over here, when we have a new moon where you go out at nighttime and it's very dark and you don't see a moon, or you might just barely see the moon, that's when we're seeing it be nighttime for the moon. We're looking at the back of, well, not the back. We always see the same side of the moon, but we're looking at the part that is experiencing night.
Wait. So we call the side of the moon that we can't see the dark side of the moon. Are you telling me it's not actually dark there?
No, it's not. It's dark to us, like we can't see it, but the quote unquote dark side of the moon experiences daylight just like the other side. It has day and night as well.
That's pretty cool. Now, not many people have ever seen that side of the moon because you'd have to be an astronaut.
Yeah, no people, in fact, just satellites.
Oh
no! Did they land on the dark side of the moon?
I don't know.
Oh,
I don't know.
orbited
the moon,
around.
Yeah, we've had people
That's
orbit the moon, but that list is a pretty short list.
It is. Okay, so there is our quick, fun little lesson on the moon and its rotation. And I hope you guys will experiment and enjoy doing some lunar art and making some sundials. I'm really curious to hear what objects you pick, because what you use to be a sundial could be anything from a lamp post to a person to a toy. You could pick pretty much anything.
And I'll say, you've got to be patient. What we found is I needed to set an alarm so that every hour we would go out and make the markings, because if you miss an hour, then I got to come back and try again the next day, because you only get your one shot. That sun just keeps moving through the sky relative to us.
It does. And you could also use a paper plate and a pencil.
So that's on
page 83.
83 of the notes.
So this is a fun version to do too, because it's a little smaller, a little more portable. And if you just color in the shadow each hour, you will end up with something that looks a lot more like an actual clock. So that's a fun way to do it as well.
All right. We get to do some math science, Mom.
But before we do, I have a where in the world question for you. You ready for this, Math Dad?
Okay, I'm ready.
I actually have two of them.
Oh.
So this national park has steep cliffs that were carved by giant glaciers. Islands here protect the kakapo and kiwi, endangered flightless birds. Do you have any idea where this is?
Okay, the first part of the clue was not helpful to me, but I hear the word kiwi, and I think New Zealand.
New Zealand is correct. Any idea what a national park in New Zealand might be called?
Beautiful. It would be called Beautiful, because that's
It is indeed beautiful, and it is called Fjordland because it is full of fjords. This is a gorgeous, just amazing national park in New Zealand, carved largely by glaciers, and there are a lot of different species of flightless birds there. The kakapo is probably my favorite. Look at that face, Math Dad. It is like a parrot that occupies a similar niche to a squirrel almost. It lives underground in burrows and digs its own burrows. Isn't that cool?
An underground bird.
Yep, it's like an owl parrot.
I like that.
Yeah. All right, you ready for the next one?
Yeah, I'm ready. All right, that was a good warm-up.
All right, our next one, I bet you will get. This rock is taller than the Burj Khalifa, and extends more than a mile underground. And if you were to walk around it, it would take you more than 3 hours to walk around it.
So this is one solid rock, continuous rock the whole way.
Sandstone. You could argue that it's the biggest rock on Earth, I think.
Wow. Okay. So that's interesting. But you didn't give me any other context clues. So I would guess it's in Australia, just because
Australia is a good guess. A couple I see in the chat, I guess, for Mount Everest, and I guess if you're going to call all of Mount Everest a rock, it would be big, but it's like different rocks. This is kind of big solid piece.
I wonder how they know that.
Noah's got it. Rachel's got it. Uluru is correct.
What? I've never heard of this. Have I?
Ayers Rock.
It is in Australia.
Yes, Ayers Rock is probably what you learned the name of, but Uluru is the more common name now, and it is enormous. From the side or from a plane, this is what it looks like. But if we get the view from space, from the International Space Station, this is my favorite view, because it really gives you an appreciation for the scale and the size. When we're looking from the side, we just think, oh, it's a long, skinny rock. But no, it's enormous.
Okay, that is pretty impressive.
And while Matt Dad is pulling up his portion of the lesson, because we do have a little bit about math today, we have some birthdays, several birthdays today. And I want to wish a very happy birthday to Amir, who turns 8 years old today.
Happy birthday, Amir.
Emily Owen, who has a birthday today. To Ethan in Illinois, who turns 7 today. Happy birthday, Ethan. And to Ruxin from Kansas, who turns 10. Happy birthday, Ruxin.
Congratulations. Another year older.
I hope you guys enjoy wonderful birthdays today. And now, Math Dad, you're going to tell us about the inverse square law. What is that?
Okay. So when I first told Science Mom, she's like, oh, we're going to do some astronomy stuff. I was like, oh, we have to do the inverse square law. And
he was so excited.
Yeah. She's like, what is this? And I had to explain it to her. But this is kind of cool. So we're going to talk about what we call square numbers. So square numbers are found when you multiply a number by itself. For example, let's fill this out together. We've got, so 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4?
16.
5 times 5?
25.
All right, 6 times 6?
36.
Yep.
And you can keep going and going.
We can keep going, yeah. So these are square numbers. Now, why in the world would they be called square numbers, though? That's not obvious at first glance, but here is one reason why. So if you draw a square, well, what makes it a square is that it has the length and width that are equal to each other. So for example, if the bottom is 8, then the top side there has to be 8, but the vertical side, 8 times 8 would be 64. So if you multiply a number by itself, you get
a square.
A square. So the area of a square. So this is one reason why we call them square numbers. And so those are useful. They show up all the time. And it's a term that you will get to know quite well. And it lets us talk about this inverse square law. On Earth, we're pretty close to the sun. We get a lot of light. But Mercury is even closer to the sun. Can you imagine what it would look like if you were to look at the sun from Mercury? Oh my goodness.
It would be blindingly bright.
It would be much brighter. And Venus is also closer to the sun. It would be brighter there. But what if you were to be off on Pluto? Head out to the far side of the solar system.
The sun's going to be a lot smaller.
That's right. It's going to look more like a star would look to us than it would look like the sun looks to us. You're going to get much less light, and relatively it would look much smaller in the sky. But how much less light is there? It turns out we can answer that question, and that's what the inverse square law is all about. So here is a picture. So think about the sun being right here, our light source, and if it heads off 1 unit here, maybe it might cover that much, but then if it went for 2 units, well, that would be the same amount of light would hit both of those, right?
Yes,
Or would reach this plane and it would reach this plane.
but it's spread out.
It would have to be much more spread out. And what if it went 1, 2, 3 units? Well, that same amount of light would get spread out even more.
Ooh.
But how spread out? So that's the cool thing about the inverse square law, is that we can quantify it. So if we go out by 1 unit, well, we get 100% of our light. But here, there are 4 squares that have to get covered by the same amount of light. Here there are 9.
Oh.
Are you seeing a pattern here, Science Mom?
So the light's going to get dimmer really quickly.
That's right. That same amount of light has to spread further. So help me out here, Science Mom. What would be the next one? If I were to do one more square back there, how big would it be? Just so it's clear what the pattern is.
Is it 16?
It is. It's 16. I guess my scale is way off here. But okay, 16 is right. So what we're able to say then is that the light here is 4 times as intense as it is right there. Or it would be 9 times as intense
as it is there.
As it is there.
Wow.
That's right. We lose the light because it's spread out further over distance. And it follows this exact rule all the time. Yeah, I'm seeing in the chat, they know that 25 will come next.
Good job, Quinn.
Yep. So actually, that brings us to my question here. All right, we've got Jupiter is 5 times further from the sun than Earth. How many times brighter is the sun's light from Earth than it is on Jupiter?
So the answer is not going to be that the light here is 5 times brighter.
Nope.
If I grew up on Jupiter and I was used to a certain amount of light and then I traveled to Earth, I'm going to say, whoa, it is, let's see, is it 25 times brighter? 25 times brighter is exactly correct. So you just took. So you take however far the distance is, whatever that number is, you multiply it by itself. So 5 times 5, and so we could say it both ways. The Earth light is the light from the sun at Earth is 25 times more intense than the light of the sun on Jupiter. Or we could say in fraction form, the light of the sun on Jupiter is 1/25 of the intensity of the light on Earth. That's pretty cool. Emraya wants to know, but what if we're on Tatooine because they have 2 suns? Oh man, Tatooine, that would get really interesting. Yeah, this idea. It would depend on how far you were from each sun, right? That's right. This law would work 1 sun at a time, but if you're combining the lights of the 2 suns, it gets a little more complicated. Yeah. But this is pretty cool. Now, I want to make sure that we have time for questions. That we're not going to run out of time. So do we want to talk real quick about an ellipse and then we'll go to our questions? Okay. I did have one more mathematical concept that I threw into today's lesson, and it's this idea of an ellipse. So an ellipse is kind of like a circle, but it's not a perfect circle. And I'll show you how an ellipse is constructed in just a moment. But yeah, it's like a circle. It's not an oval is kind of just a vague shape that's not specific. An ellipse actually has a very specific formula, but it turns out the Earth's orbit around the sun is not a circle, it's an ellipse. Sometimes we are closer to the sun at this, what we call perihelion, and we're further from the sun at aphelion, but it's almost circular. It's close, but not quite. And that actually has some ramifications on the climate and weather, but it's not something that we notice too much. That there are other forces that make a bigger difference. But how do you make an ellipse? Okay, so how would one construct an ellipse? And you can do this at home. What you'll want to do is somehow or other, you'll attach a string in 2 places. Maybe you have somebody hold it down with pencils or something. You could actually put nails in, like I've drawn here, and then you tie a string between those 2 nails, but it needs to be a loose string. You pull out a pencil, and then you put the pencil in the string and pull it tight, and then you trace the biggest
arc, you can, while holding that string tight.
Keep the string tight the whole entire time, and that will make an ellipse?
That will make an ellipse. If those two nails are closer together, your ellipse will look more like a circle. If those two nails are really far apart, your ellipse will look pretty long and
really
narrow.
Squished.
If the two nails were perfectly on top of each other, you would get a circle.
That's pretty cool.
Yeah. Ellipses are a lot of fun, and yeah, lots of explorations could be done there. But
real quick question I want to answer before we dive into our quiz questions for you guys is from Kian, and this is a great one. What would happen because the sun rises in a different place each day? And so how do you make a sundial that is accurate all year round? And if you look up pictures of sundials, oftentimes they will have kind of a board that with a lot of little marks, and there will be layers to those marks, because to read the time accurately, you actually need to know what time of year it is. So they have different layers for different times of the year. And it's true, it does change. So this sundial that we made with Math Dad, like the Math Dad peacock sundial out front, I actually want to try it again in 2 weeks and see how different it looks, because it will look different because our sun's rising and setting in different places is how we think of it. But really, the tilt of the planet as we move around the sun is causing it to change a bit.
Right. And I suspect the direction won't change as much. The lengths of the shadows are definitely going to vary over time. But yeah, I was wondering the same thing, and it's just not as accurate a tool as a clock.
Not quite. But if you don't have clocks, it's better than nothing. A quick question from Kunalin. Are there volcanoes on our moon? There are not. Our moon does not have any volcanic activity.
It doesn't have any magma. It's cooled. Is that correct?
It's mostly cooled. There is some slight movement as it continues to cool. But yeah, there are not volcanoes or plate tectonics in the moon. All right. It is time for questions. Go to itempool.com/sciencemom/live. And if you guys get all the questions right, Math Dad did record, just for you, Kara Rogers, a ballet.
All right.
We have a ballet victory dance coming. We hope.
Okay, our first question. How many days are there in one lunar cycle? So we go from new moon to new moon, or from full moon to full moon. How many days? I don't know that we said this out loud today.
We did not. So this is what we call a pop quiz. Do you know how long it takes from a full moon to a new moon?
26.1 days, 28 days, 29.5 days, 31 days, or does it depend on what month it is?
This is an interesting question.
Not all the months have the same number of days.
No, they don't. And the whole entire reason we have months, which are, a certain length, actually kind of traces back to the moon and moon cycles.
It's kind of a very natural way of measuring longer term periods of time than a day.
So if you've ever wondered, why do we have months, and why isn't a month 10 days instead of, 30-ish days? The answer is because we have a moon, and people were very interested in what the moon was doing. All right.
And 29.5 is the correct answer. 29 and a half days. So the 31 was the part that got the most values.
No, it depends on what month it is. Got the most.
Oh, you're right. Yeah. So it actually doesn't depend. The moon doesn't care about our calendars and how we are recording the time, but
it is always 29.5 days away. So I don't know, Math Dad. Do we give you a victory point for that when we didn't even cover it and it was a pop quiz?
Of course I get a victory point. Even if I ask them a calculus question, I get a victory point.
I don't think so.
All right.
But yeah, the phase of the moon does not change. It is always 29.5 days is how long it takes. And that's why sometimes you might have a month with one full moon. Sometimes you might get a month with 2 full moons.
But you'll never get a month with 3 full moons.
Never a month with 3.
All right. Next question. What time of day was in this picture? So you can just type in the time. I don't think I can take credit if you guys don't get this one right, because
it's a little tricky there.
Yeah, you don't know how to format your answer, and yeah, I bet there.
So if even one person gets it right, we're going to call it a victory for the unbeatable science kids. That's what we're saying.
Fair enough. All right. I don't know though. Maybe not even one of them will get it right.
No, I'm sure sure they will.
What time is it? Now, Kaladin always wanted to come out for our pictures, so I'm holding him.
Yeah. Oh, he can tell if we get our shoes on, and especially if someone grabs a purse and he knows that there's a car ride involved, he immediately, doesn't matter if he's been like sound asleep, if he sees like here's keys, then he'll be trotting right after us like, me too, don't leave me.
And the correct answer was 2:15.
Woohoo!
So yeah, we looked at our clocks right at the time we took the picture, and it was 2:15. So I said 2:10 got a lot of votes, 2:11, 2:20. Yeah, you guys are guessing the right region. Marmoset
is represented as well.
So nicely done. You guys understand those sundials. All right. Question number 3. Uranus is twice as far from the sun as Saturn. So sunlight on Saturn is how many times more intense than sunlight on Uranus? Uranus is 2 times as far away as Saturn.
Rebecca has a great question. Does the moon rotate around the sun, the earth, or both? And I think the best answer is both. But the first thing it rotates around is the earth. The moon is doing circles around the earth
while the earth is circling the sun.
And it turns out that our planet Earth, rotates the sun, right? Well, the sun is actually rotating around a spot at the center of the Milky Way galaxy. So we are rotating around both.
That's right. We got circles going around circles, going around circles, around circles. Yeah, it just keeps going. All right. Seeing lots of answers here. It's always trickier when it's not a multiple choice problem.
It is. You're just typing it in.
All right. And I'm going to finish and reveal. The answer is 4. So
nicely done.
Because Uranus is 2 times further, then that means Saturn gets 4 times as much light. So you have to do 2 times 2 to get that answer 4.
Good job.
Nicely done. Those of you who got that right. All right. Question number 4. If the same side of the moon always faces Earth, why do we see phases of the moon?
So which of these answers that question the best? Is it because there are tides on Earth's oceans and they pull on the moon? Is it because we only see part of the part of the moon that's facing both the Earth and the sun? Or is it because the sun rotates around the moon and this refracts the light? Or marmoset?
If you can just use the word marmoset to explain this, that would be a powerful word.
Marmosets are pretty incredible. They are.
Yeah. So what's the explanation? Why do we see phases of the moon?
And as soon as we answer this one, I'll get to K&H's question about, and they were asking exactly that. Why do we always see the same side of the moon?
All right, let's finish it up. And the correct answer was B. We only see the part of the moon that is facing both the Earth and the sun. So we can't see the part of the moon that's not facing the sun. Why is that?
We can't see the part of the moon that's not facing the Earth. We only see the same part.
Well, we understand that, but why can't we see the part of the...
Well, you can see it sometimes. It's just not lit up as bright. So if you go outside and if it's a half moon where half of the moon is bright, especially if it's a clear night and if you don't have much light pollution, if you look closely, you'll be able to see the other side, but it's in shadow. And it's not reflecting the sunlight, because the reason that we see light from the moon is because sunlight hits the moon and then reflects off, and we're seeing that reflected light. Okay, so that is actually pretty cool. So it's not that we're not able to see that part, it's just that there's no light bouncing off that part, or very little light, only starlight is hitting it and bouncing, reflecting the light to our eyes to perceive it. And why does the moon not rotate and spin around Earth? It's because it's what we call tidally locked, and that has to do with how close it is to Earth. And actually, compared to the size of a human person, the Earth is not, the moon's quite far away. It takes a long time to travel to the Earth, but it's close enough that the pull of gravity from the Earth is strong enough to keep it from rotating. That's right. One of those wrong answers previously talked about that tides on Earth were affecting the moon. It's actually the other way around. A lot of the tides coming in and out, that's affected by the moon's gravity. It's pulling on Earth. One more inverse square question. Saturn is 6 times as far from the sun as Mars. So sunlight on Mars is blank times more intense than sunlight on Saturn.
Mm.
And this really kind of drives home just how nice it is that we are in the Goldilocks zone with our planet.
Remind me about what the Goldilocks zone is.
If you're too close to the sun, then you're too hot for there to be liquid water. If you're too far away from the sun, then you're too cold. And moving just a little bit forward or back increases the amount of radiation you get or decreases it by a lot.
So it's the story of Goldilocks. Oh, now I'm too hot.
Yeah, porridge
Now
too
I'm too
hot,
cold,
too cold, and just
But now I'm just right. So
Exactly.
the Earth is in the Goldilocks zone. That is the perfect name for that, isn't
Earth
it?
is just right. And Haley had a question about what causes a solar eclipse. And that's when the moon gets in between, exactly in between the sun and the Earth. And it doesn't last for very long because they have to be lined up exactly right. And the longest a solar eclipse can be, I think, is close to 7 minutes, but that only happens like once every several thousand years, I think.
Huh.
And typical length for a solar eclipse is going to be around 30 seconds to a minute.
Yeah, great question. All right. Got 46 people who voted for one answer. They said 36 times more intense. So where did they get that number 36?
6 times 6 is
That's right.
36.
Yep, so that's what they call the inverse square law. So we square the number 6 times 6.
All right, we've got one more question in Math Dad. I think if they get this question right, then they should see the ballet dance. That's what I think.
Okay, all right. Let's do this. Okay, the dark side of the moon, so the side that's not facing Earth, never receives sunlight. Is that true or is it false? If they get it right, then you can show them the ballet dance, but otherwise, they all have to do a ballet dance for me. Send me videos.
Shyla has a great question. Why can you see the moon during the day? Because sometimes you can. You look up in the sky, you'll see the moon during the day. And that's the same reason that you can see it at night. It's especially visible if there is sunlight hitting it. And when there's a full moon and there's sunlight hitting it, you can definitely see the moon during the day as well. If there are no clouds.
But you most assuredly can't see the dark side, or not the dark side. Sorry, if it's a half moon during the day, that other half looks like it's just missing.
Yeah.
Even more, you said at night sometimes you can actually see the outline.
See the outline.
But during the day, there's so little light would be there compared to the other light sources that from the visible eye, you can't see them.
Can't see it.
All right, Science Mom, they got it right.
Woohoo!
Oh, so the dark side of the moon
is not dark.
It isn't actually dark.
Nope.
I've been lied to. Misnomer.
It is a misnomer.
Nicely done, guys.
And here we have a quick victory dance just for you guys where Math Dad attempted to do some ballet. And you might be thinking, all right, waltzing and flossing and turning around like this is not ballet. And I told that to Math Dad, and he was like, hey, I did my best.
Guys have impossibly high standards.
All right. We hope that you guys enjoy getting out and just exploring and paying attention to what happens with shadows and how our planet moves around the sun. I have to say, when we were making that Math Dad sundial, that was the first time I really noticed how much the shadow of our street lamp changes throughout the day. And it was kind of amazing. It goes from being about 4 feet long to being over 40 feet long, depending on what time of day it is. And I'd never noticed it before doing this activity.
I was impressed with how much fun it was to make the sundial. So.
It was a lot of fun. Work hard, grow smart, and we will see you next week.
Bye.